Today we will simulate tensile test in ABAQUS. So first I will create a tensile test geometry in ABAQUS. Not only the whole geometry you have to create, only the gauge section is sufficient to model a tensile test specimen when it comes to homogeneous and isotropic material. So I will create only the quarter specimen here. Now we start the model. First part 1, you can change this as tensile specimen. I will create a 3D deformable and solid specimen by extrusion, and approximate size is 200 grit. So my specimen is 40 millimeter. So 200 grit size is sufficient, or I can change to it 100 also. Continue. So this is a rectangle. I will create a rectangular specimen. Now the dimension of the specimen. Dimension is 40 millimeter in length and 5 millimeter width. And the thickness is 3 millimeter. Now the specimen is ready. Now I will give Jonson-Cook material model properties to this specimen. Mechanical, elastic. The elastic modulus for my material is 218 gigapascal. So I will take here SI units. So I am giving in millimeter. So I have to give here in MPa. So 218 and 30. And the Poisson ratio is 0.3. Now again go to the mechanical, plasticity, plastic, and hardening rule according to the Jonson-Cook. So A is the yield stress. So my yield stress is 854.0. 178.9 is the plastic modulus, and 0.86 is the value of strain hardening exponent. So if you will give the temperature property also, then you have to give here all the temperature properties of M, temperature dependent parameter, melting temperature, and transition temperature. So I am using a steel material. So for a steel material, melting temperature is 1773 Kelvin and transition temperature is 300 Kelvin. So I am not using here temperature dependent property, so I will give 0 directly. Now go to the sub option. Power law according to the Jonson-Cook. So C is a strain rate dependent parameter. So my value is 0.0083 and epsilon dot is the reference strain rate. So I am simulating at a reference strain rate by using the value of 10 to the minus 4. Okay. Okay. Now material 1 is created. So now we have to give this material property. So it is a homogeneous solid material. So this is okay. Section 1 solid homogeneous and distance. Now this specimen we have to give the material properties. Section 1 okay, distance. So now the color of the specimen is changed. You can see here. So this is the material property we have given to the material. Now assembly. In assembly, we take the specimen and we will give the independent mesh instance, or you can use also dependent mesh instance, but it is not required. So I'm giving an independent mesh to this instance. So I will shift this gauge length for the tensile specimen gauge length to this global coordinate system. So this is the instance we will try to translate from here to here. Okay. So now assembly is created and now step size is created. So I'll create a step size. I am using here a static general. So step 1 static general, nonlinear geometry is on, and the time period I'm giving 100 seconds. You can give also, this is a quasi static, you can give 600 seconds, and so this is I'm giving here initial and maximum depending upon the how many points I have required. Like I am giving a 600 second there in the basic property here 600 second. So I want 200 points. So 600 divided by 200. So 3 is the initial and maximum also I have given 3. So this is all okay. Now there is no requirement of interaction. Now in load, we will give the boundary conditions for this specimen. So I have created our quarter specimen. So for quarter specimen, axisymmetric boundary condition is required. So I am giving here axisymmetric boundary condition to this specimen. So step 1. So first I'm giving a constraint. So you can also use symmetric, axisymmetric and construct properties, or I'm using here displacement properties. So this section is constrained in x direction. So u1 is constrained. This section is constrained in z direction. So u2 is constrained. So this is process is very easy and very understandable. And here is u3. I'm checking this whether I have given this u2 or u3. So this is u3, not u2. Now I am giving velocity here. So velocity is not given in initial. Velocity is given in step first, because we have given the time period is step first. So velocity boundary conditions you have to give here. Now this is one is very very important point here. So velocity is given according to the formula that is velocity is equal to strain rate into gauge length. So here the strain rate we are simulating 10 to the minus 4, and the gauge length is 40 millimeters. So 40 multiplied by 10 to the minus 4, that is 0.0004. Okay. Now the velocity boundary condition you can see here it is applied. Now we will mesh this specimen. So first we will remove the reduced integration system. So reduced integration is not required here. Full integration you can use. And I am giving approximate global size as 1 millimeter. So very good mesh is created with approximately 600 elements. Now we will run this job and you will see the results. The paper from where I have used the Jonson-Cook material properties, I will give as a reference in the description box. Now submit the analysis. It is running. It will take 2 or 3 minutes. So you can monitor here. We will expand this, check whether it is running fine or not. Now it is running good. 6 steps has been created. So it will take some time. So we have given 600 seconds. Analysis has run up to 132 seconds. See, this is warning. Warning is given both transition temperature and melting temperature is 0. Temperature dependency are suppressed. So we have not using here temperature dependent properties. So the ABAQUS software automatically suppress temperature dependencies. And there is no error here. All the things are fine. Somewhat is slow, it depends upon the processor of your system. So if you're using a very good processor, then your analysis will run at a faster rate. I'm running it in a laptop of 8 GB RAM and an i5 configuration. So it will take some time, uh, but it is running good. So this is a step time, and step time and total time is equal. And we have given the increment size of 3, and this is 1 is 3. You can check it here. And it's very consistent. Now almost it is running and almost finished for 543 seconds and increment size of 186. So we want 200 points. So already 195 points is created and 585 seconds. Now it is good. 200 points we required and 600 seconds are run, and at a time step of 333 minimum that we have given. So you can see here one message stress is almost equal in every element. So I will plot stress strain curve from this. So at integration point, always plot stress strain curve at integration point. So I'll take this element and save it. Okay. Now I'll plot the stress strain curve. So this is a stress strain curve we have got from running the analysis. Thank you for your attention.